Hello to my fellow classmate and professor. Welcome to my today presentation that I'm going to share with you all. Today I'll present a study on my selected paper, which is shown in this slide, a millimeter wave vehicular communication to support massive automotive sensing. This slide shows my research study that contributed for today's presentations and those other supporting technical paper. These are my today agenda. Let's go to the origin of the wave history in automotive. For the past several decades, ACC system, which are using wave frequency range for radar or sensors purposes, have been the focus of research and development. Let's look at this photo. Can you guess where is the antenna is? Well, here it is. It is developed by video company in the 70s. Let's look at this photo again. Can you guess where is the antenna? Well, here it is. So, as you can see, those wireless devices are way too huge in those early days. There are several reasons, which are the microelectronics technology is still not mature enough, and the power amplifier circuit is way too big. So one of the reasons of selecting wave is that the antenna size can be made very small due to high frequencies. Let's look at the formula at the bottom of this slide, which is lambda equal to C over F. As the higher of the frequency goes, the lower of the lambda, which represents the lambda wavelength of the antenna. Let's go to the motivation. This slide shows an overview of today's radar or sensor used in the vehicle. There are three main sensors that are heavily used, which are long-range radar, and the LiDAR system, and a camera. So a typical application of using long-range radar is adaptive cruise control. Assume there's a vehicle that's on a highway. Once it sends one vehicle in front of him, which is not in the acceptable safety distance, it will automatically adjust the speed and keep the speed to maintain a safety distance. A typical application of using LiDAR system is emergency brake. Assume there's a vehicle that's driving the highway. Once it sends an unexpected pedestrian crossing the highway, the vehicle will automatically activate an emergency brake to avoid car accident. A typical application of using camera is traffic sign recognition. Suppose a vehicle is in the highway. Once it detects a speed limit sign, it will automatically adjust the speed accordingly. This slide shows the overall function and disadvantage of all those radar and sensor. They all have one very common disadvantage, which is they need line of sight detection, which have a range limitations. A question to ask, is there any way to improve the safety driving application beyond detection? The answer obviously is yes. This is where the V2V concept come into the picture to extend the car safety from detection nature type of application to prevention nature type of applications. So the typical V2V wave prevention type of application is a speed harmonizing. Suppose there's a vehicle that's driving in the highway. Once it detects a speed limit sign, it will automatically adjust the speed accordingly, and at the same time, it will broadcast and propagate this speed limit information to the car behind, which they are not able to detect the speed limit sign due to range limit of the camera. As the number of the sensor keep increasing in the vehicle, the amount of data for transmission and reception is also becoming huge. There are two possible ways to connect among vehicles. The first one is to develop a dedicated vehicle wireless network. But this method have two major disadvantages, which is network security issue, which is prone to possible hacker attack. The second one is the network coverage versus cost efficiency could be a major issue. So a V2V vehicle communication through wave technology, it seems to be a quick and visible solution for the time being. Let's go to the key idea of this paper. So this paper is proposed several challenges using wave, which is particularly using which is the beam alignment. And this paper proposed to use the DSRC technology to effectively achieving beam alignment in a better way. Let's go to the wave communications. So this is the typical overview of the spectrum usage of today's applications. In today's mobile phone, which are GSM range, which is in the range of below 10 gig. However, for mmWave, the typical frequency range is from 20 gig up to 100 gig. mmWave, which is also known as extremely high frequency. It is used for a variety of services in a wireless network, and it allows for higher data rate up to 10 Gbps. mmWave have short wavelength, which is ranging from 10 mm down to 1 mm. And last, it have offer low interference, simply because there are few applications that occupying in this very high frequency range. Let's go to the challenges of implementing mmWave. The first one is the lack of accurate mmWave vehicular channel model before 2006, and the required penetration rate of mmWave V2X capable vehicle. And lastly is lack of simple and fast mmWave bin alignment algorithm for vehicular communication. Let's go to the first one. In the case of V2V communication scenario, most of the time that both transmitter and receiver may move with a high velocity on the road. It leads to many scatter signal, which is constantly moving and change dynamically. Depending on the road condition, it can be completely open field without any blockage to an extremely busy street in an urban environment. So the number of scatter signal could vary very significantly. So the path loss and the fading channel model in the case of V2V scenario strongly influence the performance. There are three components of the loss, which are distance dependent path loss, large scale fading, and small scale fading. Given a frequency, the received power in a decimal is modeled as a formula below, as the D equal to distance, and P0 is a power level at the reference distance D0, and N equivalent to path loss exponent, and X is a large scale fading which follow a log normal distribution model, and Y is small scale fading which follow the region or relay distributed model. In the V2V channel model currently researched, which is tap delay model. In tap delay model, the impulse response of the channel is modeled with components at certain delay, or so-called tap TDL, and the average power of the tap is assumed to be decay exponentially, and the fading is implemented by varying the amplitude of each tap over time according to a specific fading distribution. As for the fading distribution, it is assumed to be using the recent fading or relay fading, and each tap may feature in an individual Doppler spectrum. In this slide, it shows the typical TDL model schematic. The XT is the original transmitted signal, and the tau value represent number of several scatter signal until L, and the G, which is represent the weight value assigned to each scatter signal, which is modeled as a region or relay fading, and at the end it performs a summation of all the scatter signal to construct YT, which represent the signal that reach at the receiver end. This slide shows the mathematical expression of the TDL model, as I had explained earlier. This H tau is the transfer function of the TDL model, whereby the GL is the component contributed by alpha and the exponential term, where alpha is the amplitude of each L tap, which is follow relay or region fading model, and the exponential term, which is governed by the scatter element in the Doppler effect. A big but. Unfortunately, this TDL model is a wide sense stationary uncorrelated scattering model, and the region and relay fading are based on assumption that all magnitude of scatter signal that go through the channel and the channel fading are region or relay distributed, and all the scatter signal are uncorrelated. But this is not the case when it comes to V2V communication channel, whereby two scatter signal could be correlated to each other. So this TDL model may not able to accurately estimate the V2V channel. So the research is still continue. Now let's go to the last one, which is a lack of simple and fast mmWave bin alignment. So why MM wave need bin alignment? Typically, the frequency for MM wave could be reaching 60 plus gig. So it suffers from a large attenuation. Let's look at this free space propagation loss model. As you can see, the higher value of the frequency go, the lower of the received power at the receiver end. So how do we boost this radio signal in the MM wave? So instead of transmitting using an omnidirectional antenna, which is commonly used in our home wireless network, the MM wave RF signal energy can be increased by compressing the isotopic radio energy and project it in a restricted angle of direction, which in this case is directional antenna, which also in terms of Yagi antenna. Since the MM wave made the antenna length to be very small, it can build an array of antenna to project and transmit the RF in a various angle of transmission. It is called a beam forming. Since both transmitter and receiver beam need to be aligned properly in order to make proper connections. Suppose there are two vehicles try to make connections. Since the RF energy is only projected in a limited angle, so both beam from a transmitter and receiver need to be aligned properly to make connection. An exhaustive search of the beam location is too time consuming. Suppose we have n number of TX and RX antenna. A typical beam alignment process is, suppose antenna TX1 is activated and each of the RX antenna are activated consecutively, and each RX antenna will send its own obtained SNR value back to the transmitter side, and this process proceeds to the next TX antenna and so forth. This searching complexity is n power of 2. In the IEEE 802.11ad, it is a proposal method. It reduces the complexity down with a ON. Suppose that the initiator have a 8 TX antenna and the responder has 3 RX antenna. All of the RX antenna are activated at the same time, and each TX antenna from the initiator will transmit consecutively. The responder will then send acknowledgement with the SNR value back to the initiator. The initiator will receive the acknowledgement from the responder and then find the best receive and transmit antenna with the best SNR value. Let's go to the improvement by this paper. So the idea is to able to use the relative position information obtained from a DSRC connections and utilize that information to restrict the beam searching angle. So let's dig a little bit deeper in the DSRC operations. A typical DSRC operation involves each DSRC equipped vehicle. It will broadcast its basic state information, including location, speed, and acceleration. And each vehicle also receives this safety message from DSRC equipped surrounding vehicle. And then it will compute the trajectory and estimate possible collision threat. This DSRC is following the 802.11a standard, whereby it has a header called the WSM, which is a wave short message. In this extension field of this header, it contains a 2D locations information, which is an 8-byte field conveying the location of the transmitting device, encoded as a 32-bit latitude and longitude, with the 0.1 microdegree resolution, and also it contains a 3D location as well. So this advantage of DSRC technology is the data rate is only up to 54 Mbps, compared to MM wave, which data rate can up to 10 Gbps. The ultimate goal is to use the DSRC to obtain relative 2D and 3D location information and discard those antenna that are not possible to achieve the best SNR, hence restrict the number of antenna searching space. And then finally, it will switch to MM wave connection instead of DSRC. Let's go to the evaluation. So let's look at this graph below. As you can see, assuming is using 8x8 or 16 by 16 UPA, which is called uniformly planar array. So if using these two UPA, the number of antenna searching attempt could be reaching 552 or 3000 plus beam training attempts. But with the use of this DSRC method, the number of beam training is greatly reduced below 18th attempt. So, but the author did not include a total overhead of the header forwarding and switching between DSRC to mmWave. So the advantage of this method is it can speed up the beam alignment process provided the DSRC connection is established first. If we disregard the overhead for DSRC connections, and the disadvantage is it expensive because it needs both DSRC and mmWave hardware devices. Thank you for your time. This is the end of my presentation. Thank you. Bye.